And now we're going to talk about section R7, which are called radical expressions. So we did talk a little bit about radicals before, and just so we're all on the same page, that's what a radical is. Now you could take the square root, the third root, whatever number that is called the index. And whatever number goes here, like the cubed root of 8, 8 is called the radicand. All right, just so we all have the same terminology. And the property we've talked about so far is with rational exponents. We said that if we have a fractional power like this, we said that we could think about it one of two ways. One way is we could think about it as the nth root of a to the mth power. And that's the way we mainly did a lot of these problems. It's just easier to do in our head. But equivalently, we could also think about it as the nth root of a to the m power like that. So what I wanted to do now is let's just practice converting from radicals to and from rational exponents. And an exponent is just another word for a power. So what that means is we're taking radicals and we're turning them into powers and vice versa. So for example number 1, we have a to the 2/3. And from the properties we just talked about, we could think about this as the cubed root of 8 to the second power. The cubed root of 8 is 2. So then 2 to the second power, of course, is 4. What about if we had 2p to the 1/2 power? Well, the power of 2 is really 1, so that doesn't change. I mean, 2 is fine just the way it is. But p to the 1/2, we could write the second root or the square root of p to the first power. So we know that a square root is the same thing as just leaving a radical by itself. That means the second root, or you could actually put a 2 there if you want. What about if we had 3a plus b to the 1/4 power? Well, I mean, the rule is what it is, right? It says that anything to a fractional power means we're going to take the 4th root of whatever's on the inside all to the first power, right? So math is all about rules. If you follow the rules, you'll get the right answer. The 4th example says, let's write the 4th root of x to the 5th as rational exponents. So according to the rule, this is always the denominator of our fraction, and the 5 would go on top. What about if we had 10 times the 5th root of z all to the second power? Now the 10 is fine the way it is, so we'll just leave it alone. But when we have the 5th root of z to the second power, that comes into our properties over here. That's actually this property, right? And we could just write that z to, the index is always going to be in the denominator, and the 2 would be on top. One last example like this. What if we had the square root of p squared plus q? Well, this is really the second root of this whole thing to the first power, right? So we're just kind of filling in numbers that we know are there. So we could write this p squared plus q all to the 1/2 power. So that's how we go back and forth from radicals to rational exponents. The next thing I wanted to talk about is the importance of absolute value when we're discussing this. Not disgusting. It's not disgusting. It's actually kind of pretty. I joke with my students that, some people say that Italian or French, those are love languages. I consider pre-calculus a love language, so it's not disgusting, but I meant to say discuss. Let's discuss absolute value and its importance with radicals. So the rule with absolute value is that whenever you take an even root of anything to an even power and you get an odd power answer, you need absolute value. So you need these three things. 1, 2, 3. Even, even, odd, you need absolute value. That's the rule. If one of those are missing, you don't need absolute value. So let's take a look at a few examples. What about the square root of p to the fourth? Well, a lot of the times when we're working with radicals, we convert them to rational exponents. This is really p to the 4 over 2, or p to the second. So we have an even, even, even. So we don't need absolute value. What about if we had a problem like this? Say we had the square root of, let's say, x to the second. All right, we'll just make it easy. Well, it's really the second root of x to the second. So according to our properties, we could write this x to the 2 over 2, or x to the first. This is even, and this is odd. So anytime you take the square root of anything squared, you have to have absolute value. If you don't include absolute value, you won't get one of the answers. All right, a couple more here. What about the square root of 16m to the 8th r to the 6th? Well, this is really 3 square root problems. You could break up a radical like this. The square root of 16 is 4. The second root of m to the 8th is m to the 8 over 2. And this would be r to the 6 over 2. So we get 4 m to the 4th r to the 3rd. Well, in all these cases, it's an even root, even power, odd answer. That needs absolute value. Even, 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 we don't need absolute value there. And anytime you take the square root of a number, it's always just a positive answer. Square root of 25 is just 5. Square root of 4 is just 2. Last problem like this. What about the square root of x squared minus 4x plus 4? One thing that you don't want to do with radicals is you don't want to distribute it. You can't just do this. That's like really bad math. You don't want to do that. I tell my students in high school that if you do that, when you go on to your next math class, and if that teacher ever tells me that you did that, I'm going to deny ever teaching you. So that's like a really, really bad mistake. The way that you do a problem like this, you could distribute radical over multiplication or division, but if it's addition or subtraction inside, we have to factor. And remember how we talked about factoring in a previous lesson? We said you multiply the AC. You have to add up to be negative 4, so we could use negative 2 and negative 2. And eventually, as you factor, you could start to figure out your own shortcuts. But if any of you are a little bit rusty on factoring, I'll show you all the steps. So really, what that turns into is just x minus 2 times itself, right? So this is really just the square root of x minus 2 to the second power, or x minus 2 to the 2 over 2, or x minus 2 to the first. Well, look what we have here. That's an even number, odd answer. You need absolute value. So sometimes the answers could look a little funny, but that's just the way it is. So let's move on to talking about how to simplify radical expressions. Okay, well, first example looks like this. Let's say the square root of 6 times the square root of 54. Now, there are many different ways to do a problem like this. I'll show you the way that I found from my experience that most students think is the easiest. One thing that we could do is we could just multiply these numbers together. That's the square root of 324. And then from here, we're going to break down this radical. The way that I teach it is with a prime factorization tree. And what that means is we break 324 down to prime numbers. Now, the smallest prime number is 2. So this would be the same thing as just 2 times 162. 2's prime, so let's break down 162 more. 162 divided by 2 is 81. And at this point, some teachers tell you to stop. 81's a perfect square, but what I do is I just keep going until all of the bottom rungs of my ladder are prime numbers like this. And I'm looking at these bottom numbers. Now to simplify a radical, this is a square root, so we're looking for groups of 2. However many number of groups you have go on the outside of the radical, and whatever's left over goes on the inside. So how many groups of 2 of the same numbers do we have? Well, here's a group of 2 of the same numbers. There's one group of 2. Here's a group over here of 2 of the same numbers. And here's another group. There's nothing left over. So as far as what the answer would be, it's just 2 times 3 times 3. 9 times 2 is 18. What about a problem like this? The fourth root of a over b to the fourth. With radicals, we take the radical of the top part of the fraction and the bottom part of the fraction. Can't do anything with the fourth root of a. That can't be broken down anymore. But the fourth root of b to the fourth is really just b to the 4 over 4, or b to the first power. But we have an even, odd situation here, so we need absolute value on that b. You don't have to put the 1 if you don't want, but that would be the perfect answer. All right, and then one more. What about if we got a little crazy here and we said the 7th root of the 3rd root of 2? All right, so what we could do with this is let's convert to rational exponents. So the cubed root of 2 to the first, this piece would just be 2 to the 1/3. And we're taking the 7th root of that, right? We just converted that inside radical. Well, 7th root is really just 2 to the 1/3 to the 1/7 power. When you have a power to a power, you multiply. So this is 2 to the 1 over 21, or the 21st root of 2. So we're just using a bunch of different properties here. All right. Let's get a little bit more into how to simplify non-perfect radicals. And we talked a little bit about this before with our prime factorization tree. So the square root of 8. There's really 2 techniques that teachers teach. One technique that they teach is what I showed you before, where we just keep breaking 8 down to prime numbers, and then our answer we would write, our groups go on the outside, and whatever's left over goes on the inside of our radical. So this is square root. We're looking for groups of 2 of the same numbers. So look at your bottom rungs of the ladder here. Here's a group of 2. One group of 2, and there is just this leftover 2 hanging out over here. So our answer would just be 2 root 2. That's the answer for this. Now another way some teachers teach, it's not wrong, but I found the prime factorization method where my students prefer that, is to take the square root of 8 and break it down to perfect squares. So for example, I know that 8 is really 2 times 4. So the square root of 8 is really just the square root of 2 times the square root of 4. The square root of 4 is just 2. And that's the same thing as the answer we got over here. I'm going to be using my prime factorization tree. Just from my experience, that's what most students prefer, but if you like that second way, feel free to do it that way. How about the square root of 175? All right, well, let's think about what goes into 175. Definitely 5, right? So this would be 5 and 35. 35 could be broken down to 5 and 7. And we'll do what we did before. we're looking for groups of 2 of the same numbers. Here's a group of 5, one group of 5s, and then there's a 7 left over. So that would be the answer. And then our last problem, let's get a little creative with this one. Let's say the third root of 81, x to the 5th, y to the 7th, z to the 6th. This is really 4 different problems. So we'll do the cubed root of 81, we'll do the cubed root of x to the 5th, we'll do the cubed root of y to the 7th, and we'll do the cubed root of z to the 6th. Well, the cubed root of 81 is just 3. Actually, no, it's not. 3, let's see, right? So 81 is really 9 times 9. The cubed root of 27 is 3. But if we keep breaking it down to all prime numbers, we're looking for a group of 3 of the same. Well, here's a group, and we have a 3 left over. Remember, that's a third root. What about this one, right? So we're looking for groups of 3 of the same. So x to the 5th is really just x times itself 5 times. So how many groups of 3 are there? Well, here's a group. There's one group of x's, and then it looks like there's 2 left over. Same thing with y to the 7th. We're looking for a group of 3. So actually there's 2, right? So there's 2 groups, and then there's just 1 left over. And then the z to the 6th, well, that's just the same thing as z to the 6 over 3, which is 2. We don't need absolute value because it's not even, odd. So let's combine all of these answers here. Let's write what's on the outside. 3x y squared z squared times the cubed root of 3x squared y. That would be the final answer. Now what if I asked you, instead of doing the cubed root of y to the 7th, what if I asked you what's the cubed root of y to the 29th or something? You don't want to write out y 29 times. That would be kind of annoying, right? So think about what we did over here. How many times does 3 go into 7? 2, right? With a remainder of 1. Well, how many times does 3 go into 29? 9, right? So it goes in 9 times. Oops. With a remainder of 1. Well, look at this. 2, right? And that turns into this number. Remainder of 1, that turns into this number. So the way that we could write this, we could say y to the 29 over 3 as a mixed fraction would be, goes in 9 times with 1 left over. So sometimes people prefer to simplify these not by making prime factorizations, but by using improper to mixed fractions. So as far as what the answer would be, the cubed root of y to the 29th would be y to the 9th. That's how many groups of 3 there are. But then there's 1 left over. That was the remainder. And that could be how you do it, right? So looking at the problem we just worked on, the cubed root of y to the 7th, might have been a little bit faster if we just said y to the 7/3. 3 goes into 7 twice with 1 left over. So using our property that I just showed you, the answer would be y to the 2nd times the cubed root of y to the 1st, which is the same thing that we had over here. So I like showing different ways to do these problems. Okay, let's talk about how to add and subtract radicals. Now, in order to add and subtract radicals, we need to have the same indices. Indices is plural form of index. And the same radicands, meaning what's on the inside of the radicals. So let's take a look at an easy problem first. What if we had 3 times the 4th root of 11pq minus 7 times the 4th root of 11pq? We have the same indices. We have the same radicands. So let's combine them, right? If you have 3 apples minus 7 apples, you have -4, right? I mean, you can't really have a -4 number of apples, but they're like terms. So we would have -4 fourth roots of 11 PQ. That would be how you reduce this. Sometimes you have to simplify the radical first. So like, let's say if you had the square root of 98, x to the third y, plus 3x square root of 32xy. Let's simplify these first. Square root of 98, well, this is just 2 and 49. So I'm going to use that second way. That might be the fastest. The square root of 49 is 7, so we get 7 root 2. This would, the square root of x to the third. I know that 2 goes into 3 once with 1 left over. So x to the 1 and 1/2 would give us an answer of x with the square root of x to the first. And then we have a y, right? So fully simplified, that radical would be 7x square root, let's see, I forgot the y, 7xy, the square root of 2x, plus, we're going to do 3x times whatever that simplifies to. Square root of 32, this is just 2 and 16. You could keep factoring if you want, but the square root of 16 is just 4, and then we have the square root of 2. And we can't do anything with the x and y. Those stay inside the radical, and we have the 3x on the outside. So really this turns into 3x times 4, 12x, square root of 2xy. And that's nothing we could really do after that. Let me see here. Did I make a mistake? The y was inside of the radical for over here, so I just put it outside. I shouldn't have. We'll keep it inside. And we could see that we have the same index for both square roots with the same radicands. So 7x plus 12x would be 19x square root of 2xy. Let's move down to simplifying some more radicals. So say we had a problem like this. 6th root of 3 to the second. When we talked about doing this, a lot of the times it's just easier to write it as a rational exponent. 2/6 is really just 1/3. So this would just be the 3rd root of 3 to the first. So you could see that we use a lot of different properties, so it's important that you commit those to memory. What about the 6th root of x to the 12th, y to the 3rd? Okay, well, this is really just x to the 12 over 6, and this is y to the 3 over 6, which is x to the second, y to the 1/2, or x to the second times the 2nd root of y to the first. If you know your rules, you're fine. And then the last one, what about the 9th root of the square root of 6 to the third? So I always kind of like these problems. Now this part right here, the square root of 6 to the third is really just 6 to the 3 over 2 power. Then we're taking the 9th root of that. The 9th root is really just 1 over 9. When you have a power to a power, you multiply those. So 3/2 times 1/9, well, 3 goes into 9 3 times, so this would be 6 to the 1/6 power. I just multiplied 3/2 times 1/9, power to a power. The answer would be the 6th root of 6 to the first. Next, let's talk about how to multiply radicals. When we're multiplying radicals, it's the same thing as with anything else, but you want to multiply the outside numbers. So let me say it like this. If the indices are the same, then you multiply the outside terms and you multiply the radicands. So I only have one example with this. Let's take a look at like the square root of 2 minus the square root of 3 times 2 radical 3 minus 4. So this is really just a FOIL problem, right? So 1 root 2 times 2 root 3, I'm going to multiply the outside numbers, and I'm going to multiply the inside numbers. I'm going to multiply the last terms. So the 4 doesn't have any radical, right? So I'm just going to multiply 1 times negative 4. And then the square root of 2 has nothing to be multiplied with. Multiply the inner terms. Negative 1 times 2 is negative 2. Square root of 3 times square root of 3 is 9. And then negative 1 root 3 times negative 4 is positive 4 root 3. So let's clean this up. What do we have here? 2 root 6, there's nothing to simplify. 6 is just 2 and 3, there's no groups. Nothing. Square root of 9 is really 3, right? So we could write it like this. 2 square root of 6 minus 4 root 2 minus 2 times 3 plus 4 root 3. And the best answer would just be 2 root 6 minus 4 root 2 minus 6 plus 4 root 3. There's nothing to simplify or combine, that's it. I wanted to talk a little bit more about fractions, specifically how to rationalize denominators. And really what this means is we want to match the denominator's power with the index. So in math, there's a such thing as manners. Just like if you're going through a door, you don't let it slam shut on the person behind you. That's just having good manners. In math, we don't want to have radicals in the denominator. And the way that we stop that from happening is we match their powers with the index. Let me show you what I mean. What if we had 4 over the square root of 3? Well, we don't want to have a radical in the denominator. That's bad manners. So this is really the second root of 3 to the first. I want to make the power of 3 match the index. The way that I could do that is if I multiply by the square root of 3 to the first over the square root of 3 to the first, look what happens to the bottom. 3 to the first times 3 to the first is 3 to the second, and that matches with the index. So the numerator would stay 4 root 3. We don't really care about the numerator, but the bottom, the square root of 3 squared, these would cancel and you just get 3. That's how you rationalize a denominator. What about something like this, the 4th root of 3/5? So let's break this up. We'll take the 4th root of 3 over the 4th root of 5. Now we want that 5 to match the 4, right? So this one, we want to make it into a 4. So in order to do that, we'd have to bump it up by 3. Multiply by the 4th root of 5 to the 3rd power over the 4th root of 5 to the 3rd power, which gives us 4th root of the numerator would be 3 times 5 to the 3rd. 5 to the 3rd is 125, and 125 times 3 is 375, which we can't simplify. But the denominator would be the 4th root of 5 to the 4th. The whole idea is that cancels out the radical there. And that would be the best answer. How about a problem like this? Like 1 over 1 minus the square root of 2. Now we can't have a square root in the denominator, but if you've ever been to Chuck E. Cheese, like the game store, you'll know what I'm talking about. If you don't have to write this down, just think about it. If we multiply by the square root of 2 over the square root of 2, when you go to distribute it, it'll cancel out that radical. In the denominator, you would get minus the square root of 4, right? So that would cancel out the radical, but it would show up over here. So it's kind of like that whack-a-mole game. If you multiply by the radical, it disappears one place, but it shows up somewhere else. So if we have a binomial in the denominator. If there's two terms in the denominator, one has a radical or both, what we could do is we can multiply by what's called the conjugate. Conjugate just means it's the same thing, but we change the sign of the middle. This is kind of like outsmarting the problem. So we don't care about the top. We'll just distribute this. This will be 1 plus root 2. But look what happens in the denominator. If we were to FOIL this out, we get 1 plus root 2 minus root 2 minus the square root of 4. So these cancel. That always happens. And you just get 1 plus root 2 over 1 minus the square root of 4. 1 minus 2 is just negative 1. So, I mean, really the best answer would be negative 1 minus root 2. Let me show you one more advanced one, and then we'll just finish with 2 other types of examples here. Sorry, this is a long lesson. There's a lot to cover in this one. Square root of 2 over the square root of 2 plus the square root of 3. Again, we'll use the conjugate of the square root of 2 minus the square root of 3. We don't care about the top. It's just going to be the square root of 4 minus the square root of 6. In the denominator, we'll get the square root of 4 minus the square root of 6 plus the square root of 6 minus the square root of 9. These cancel. The top is just the square root of 4, which is 2, of course. So we get 2 minus the square root of 6 over 2 minus 3, giving us the answer negative 2 plus the square root of 6. Let's take a look at one more here, one more type of problem, and then that'll be it. So simplify radical expressions with fractions. First one is the 4th root of xy to the 3rd over the 4th root of x to the 3rd y to the 2nd. So first thing let's do is let's simplify. So just like we could break up a radical like we did over here, we broke it up to the top and the bottom, we could actually combine the radicals. So just make one big happy 4th root of x y to the 3rd over x to the 3rd y to the 2nd. Let's simplify this first. Get the 4th root. X to the 1st divided by x to the 3rd would be x to the negative 2nd. Y to the 3rd divided by y to the 2nd would just be y to the 1st. And we talked about bringing this down. We just get the 4th root of y divided by the 4th root of x to the 2nd. Well, now let's continue our conversation from the last type of problem. We really just want this to be the same, right? So let's multiply by the 4th root of x to the 2nd, because by doing so, we don't care about the top, but the bottom becomes the 4th root of x to the 4th, and they cancel, which is the whole idea. So you just wind up with the 4th root of x squared y over x. And our final problem for this section, what if it's the 3rd root of 5 over x to the 6th minus the 3rd root of 4 over x to the 9th? Well, if we break this up, the 3rd root of 5 divided by the 3rd root of x to the 6th minus the 3rd root of 4 over the 3rd root of x to the 9th. This is really just x to the 6 over 3, which is 2, right? Just make sure your index looks like an index. This would be the cubed root of 4. The cubed root of x to the 9th is just x to the 9 over 3, which is x to the 3rd. All right. And as far as the radicals, I mean, they're taken care of, but generally whenever we have two fractions, we always want to combine them to one. And talking about our least common denominator, that would be x to the 3rd. So we just multiply this fraction by x over x, we would get x times the third root of 5 over x to the third minus the third root of 4 over x to the third, or we could just combine both of those fractions. All right, so thanks for following along. Stay tuned for the next lesson.